Welcome to Designing an Optimized Voltage Divider Bias BJT Common Emitter Amplifier. In this section we're going to focus on adding some AC components and overall voltage gain. So in part 1 we designed the optimized universal biased DC circuit for our amplifier. And optimized, we should have 45% of VCC at RC, 45 at VCE, and 10% at VRE. And hopefully you've got that built and it's measuring very close to what you calculated. In this section we're going to start looking at gain. So the gain of an amplifier is basically the output voltage divided by the input voltage. So here's our circuit with our added VGen or generator and our load resistor. And you notice we've used two coupling capacitors, C1 and C2. And for this example, we're going to use 10 microfarads for those capacitor values. And in part 3, the frequency response section, you're going to see how the value of the coupling capacitors affects the frequency response of the amplifier. So why use these coupling capacitors? So what capacitors do is they pass AC signal, they act like a short to AC, and they'll block DC. They'll act like an open to the DC. And so what that does is allows us to throw that load on there on the circuit, couple the load to the circuit, and couple the generator to the circuit without affecting our original bias circuit, the universal bias circuit. And that essentially keeps all of our DC voltages the same. So our biasing voltages stay exactly where they're supposed to be, and they're unaffected by adding the load or the generator. Okay, so we're going to shift gears a little bit here, and we're going to start looking at the circuit from the perspective of AC. So to AC, the coupling capacitors look like shorts, and also the DC generator looks like an AC ground. There's a big filter cap right in the front of that DC supply that basically sends the AC straight to ground. So the AC sees the DC voltage supply as a ground. And so now thinking about our gain formula, delta V is equal to V out divided by V in. We're going to start using Ohm's law to kind of find something that represents V out. So here we have a picture of an AC redraw from the collector out, basically the load. And we can see that voltage is in parallel there, right? And so we've got the same voltage hanging there at the collector all the way to the load. That's going to be the same voltage. We don't have the current out. We don't know what IL is, or even the current through the AC current through the collector resistor. But we do know that we've got an IC hanging right here off the collector that's going to be changing. It's going to be a delta IC as there's base current is changing. The collector current is also going to be changing. And so if we use Ohm's law, we could say, okay, let's take RC in parallel with RL. That gives me an equivalent resistance that's hanging off that collector. Now I can use IC times a resistance, and that would give me a voltage according to Ohm's law. So here we have the redraw that shows basically what Vn sees and the current paths for Vn. Now one thing we need to just know here is that there's an R prime E the AC base to emitter resistance. Now that resistance is just inherent to the transistor, and it's going to live right there in that base to emitter area. And in order to calculate that resistance of R prime E, it is 26 millivolts divided by IE. So in my example, my IE was 4.545 milliamps. So divide that into the 26 millivolts, that gave me 5.721 ohms. Now, I want to get the resistance on the other side of the beta barrier. And we can do that just like currents can move across the beta barrier. So we've got an IB here on the base, and we've got an IE on the emitter. And we know that IE is equal to IB times beta plus 1. So if you think of Ohm's law, if you're moving from a low current side to a high current side, or high current side to a low current side, you've got to keep the resistance in the same ratio. So we want to move our resistance RE and R prime E to the other side of the beta barrier. So we're going from a high current side to a low current side. So if current goes down, we know that resistance would need to go up according to Ohm's law. And in this circuit, it would need to go up by a factor of beta plus 1. So we're going to move that resistance to the other side of the beta barrier, and that gives us the AC redraw that has the box around it. So now we've got the equivalent resistance here. We want to find this voltage, or something that represents this voltage Vin here. So we can see now we've got Vin. All these are in parallel, but if we put them all in parallel, we don't know have anything that represents In, which would be right there where the generator is. But we do know or have an equivalent IB here. And so we know that IB, this current right here, times this equivalent resistance would give us the voltage, or a voltage that represents Vin. So that gives us our R prime E, the final formula that's at the bottom of the page, the R prime E plus RE brought across the beta barrier, that resistance times IB gives us something, a voltage that represents Vn. So now we have two formulas, one that represents V out, that's in terms of resistance and current, and one that represents Vn, that's also in terms of resistance and current. Now, the currents that we're talking about are AC currents. And that's where the delta is representing a change in IC and a change in IB. Now we can factor out that delta and cancel it. And because they're both changing at the same rate and they have the same relationships. So mathematically, we're going to factor out the deltas and then cancel them. And now we can use our IC and our IB, our DC IC and IB, which are values that we know, and our resistor values we know. So now we've got it all down to fixed terms that we already know, and we can actually calculate the gain of this circuit. And in my example, after doing all the math here, I got a gain of minus 2.193. So the question is, well, where'd the minus come from? Well, with the common emitter amplifier, the output is out of phase with the input. So the only thing the minus represents is that 180 degrees phase shift. So if you see a common emitter amplifier, it should have a minus gain. The calculations are all absolute. The minus just represents the phase shift, 180 degrees out of phase shift. So maybe a gain of 2.193 is exactly what you wanted, and the circuit would work perfect for what you want. But maybe you want a little bit more gain than 2.193. So how do we change the gain in the circuit without affecting the DC biasing? We've got to keep our biasing exactly the same. So the way to do it is to look at V in. So we've got our V in kind of AC redraw here. And what we're going to do is, the gain is V out over V in. So if we can decrease V in, we can get more gain. So one way to do that is to use a bypass capacitor. So you can see here we've got C3, the 10 microfarad bypass capacitor. So now to AC, we basically have eliminated RE. There's a short to ground right there. So now we're just going to bring R prime E across the beta barrier and then multiply that by IB. So we've reduced that emitter resistance significantly. So here's our original formula. And you can see with the bypass capacitor, we've eliminated RE. So AC does not see RE with that bypass capacitor right there. So now we've got R prime E brought across the beta barrier. We're going to multiply that by IB. That gives us our V in. So our V out effectively stayed the same part, that circuit part. Now we can see, using those numbers for my circuit, now I have a gain of 86.532. So that's a huge gain and a huge difference from the 2 point whatever it was before. The problem with a lot of gain in one stage is you're going to get some distortion. The device can't keep up with, the output can't keep up with the changes on the inputs because it's having to change so much. So a gain of 86 is too high for a single stage. So really you want to stay at a gain of 20 or less. And if you need a gain of 86, add a second stage. So I know with no bypass capacitor, I can achieve a voltage gain of minus 2.193. And with the emitter resistor fully bypassed, I can achieve a maximum gain of minus 86.532. So let's say I want a gain of minus 10, which is between those two extremes. What I can do is I can split RE into two. So I've got an RE1 and an RE2. And based on that ratio, I can get the gain of 10. Now what's important is to make sure that when I split the two, that I still have the same original resistance. In my case, it was 220 ohms. So they both need to add up to whatever your RE was in order to maintain your DC biasing, because you don't want that to change. So with a desired voltage gain of 10, we can work our derived formula backwards to solve for RE1. And we're going to do that in the next slide. So here's our formulas from before. We've got our minimum gain, and you can see with our minimum gain, we've got the full RE, the unbypassed RE. And that gave us our minimum gain. For the maximum, it was our RE was fully bypassed with the capacitor, and so we don't have any RE in that formula. And that gave us our maximum gain of 86. So we want a gain of minus 10. So we're going to work backwards. We're going to say, okay, our gain is minus 10. We're going to drop in our formula, we're going to add in the RE1. So the RE1 is going to be our one unknown. So we can do some algebra here and solve the formula for RE1. And you can see I've got the steps here. Once you've got it solved for RE1, now you can put in your known values and solve for your actual RE1. And so in my example, my RE1 calculated out to 44.234 ohms. Now we've got RE1. Next, we need to figure out what the value of RE2 is. So we know what our total emitter resistance should be based on what we calculated back in part 1. For my example, it was 220 ohms. So 220 ohms minus RE1 should give me RE2. In my case, 220 minus 44.243, I get 175.766 for RE2. So now we've got a final circuit. We've got a universal biased, optimized, common emitter amplifier with a gain of minus 10. So let's go back and make sure that our bias circuit is 100% correct. Let's go back and measure all of our DC components. So as far as the gain though, let's wait to measure the gain until after we complete part 3, because there's a few things we need to know. We need to know frequency response, and we also need to know the AC/DC load line is going to give us our V out max and our V in max. So we don't really know frequency response and the maximum input and maximum output values yet. But it's important to go back and make sure our DC, because we've changed a few things in the emitter resistance, let's make sure that we're still measuring accurately on the DC bias part. So in conclusion, for part 2, we just use a lot of algebra in Ohm's law. And for me, I really like to derive my own formulas. I like to look at it and say, okay, well, I know gain is out divided by in, V out divided by V in. So how do I derive? How do I find something that represents V out? How do I find something that represents V in with what I know? Okay, a couple of formulas that you're going to need to memorize: the AV, keep it simple, V out over V in. That's the only thing I want to remember is the gain for gain formulas, V out over V in, and then I'm going to derive those other two components. R prime E, you kind of just need to memorize that one. It's 26 millivolts divided by IE. And we saw that with no emitter bypass capacitor, AV or delta V, the gain will be minimum. And with the emitter fully capacitively bypassed, we're going to see the maximum gain. So in order to achieve the gain that we want, we can split RE into RE1 and RE2, and we can get anything between that minimum and that maximum by changing that ratio. But it's important to make sure that RE1 and RE2 still add up to RE, because we don't want to change our DC biasing at all. And then finally, after we have calculated the circuit with the gain that we want, we need to go back and verify our DC biasing is still good. And we're going to measure the AC components after we complete part 3.